to the Assured interview series, in which we are talking about the future of security in next-generation smart connectivity systems, comprising heterogeneous IoT and other types of cyber-physical systems. I'm Claudia dos Santos from Martel, and I'm here today to learn more about Assured, a Horizon 2020 project dedicated to safeguarding the operational assurance of IoT systems. With me today is Ahmed from Systems Security Lab at TU Darmstadt. Ahmed and his team are the technical contributors to Assured, actively researching runtime and behavior attestation of devices and IT systems. Welcome, Ahmed. I'm glad you could join us today to tell us more about your lab's work within Assured.
Thank you.
So let's start. Could you start by telling us about the most urgent problem in cybersecurity research that you're currently addressing in Assured?
So I think one of the very urgent problems in cybersecurity in general and in specifically in Assured is how to verify the integrity of any computing system. So if you have a software running on any computing system like servers, desktops, laptops, how do you assure that this software has not changed, has not altered, has not been manipulated by any adversary? So in general, we would like to have efficient and effective methods to verify the integrity of this software. And this software can be a simple software, for example, for small systems like a sensor. It can also be a very complex software like a browser that we use every day. So if the browser is attacked, then we would like to at least have a mechanism to check that. And I think this is a very general problem, and we are looking into a specific part of it in Assured.
And could you walk us through the philosophy behind trusted computing attestation services and the position of control flow attestation?
Yeah, trusted computing is a general concept that was introduced some years ago. Specifically, many IT enterprises were interested in securing their legacy systems, the systems that we are typically using. And in the course of time, people understood that these systems have not been made with security in mind. And so there were lots of attacks, and these attacks are still persistent, even more than 3 decades. So the legacy system had a problem. So the question was, are we going to change our legacy systems based on the lessons that we learned, which would be extremely hard and not really efficient and costly. So many companies in commercial area, but also in academia, millions and millions of code lines were written in insecure languages like C and C++. But also if you have other languages that are type safe, still they are running in legacy-based emulators and interpreters and whatever. So it is not easy to replace everything with from scratch designed for security. So what trusted computing idea was that can we add, so very simply and roughly explained, can we add new components which are trusted? That means there are small components in hardware and software in general that we add to a system, and they allow us to provide more complex security features and fulfill more complex security requirements. But the condition is to trust these components, but these components should be small enough so that they can be verified by means of technologies that we know, like software verification or hardware verification. So they should not be complex, like an operating system, for example. This was the idea. So having a small set of trusted components, can we build secure systems using legacy systems? So of course the idea is good, but in practice this is not something that today we can say we really kept those promises. So the promises are only partially kept and partially there's a partial success there. So this is the idea of trusted computing. So you trust certain components and you build secure systems around it. Now, the question is, what is attestation here? Attestation is a functionality of trusted components, because if you have a trusted component in your system, you also trust that this component will report to you if any changes has been done on your system. Doesn't matter if you do it, these changes, or any external party, any changes that would touch the integrity of the system. So this is attestation, which is a mechanism that allows a party from a remote distance to verify a computing system, whether or not this system has been changed in any sense. It could be software. There are also ideas how to check the hardware. So indeed, it is not really trivial to do that. There are simple cases that you can do that, which was proposed by industry. But in reality, we have many new attacks, at least in the last 10, 15 years, that they become state of the art. These attacks are called runtime attacks. They bypass the conventional attestation mechanisms. So you cannot really recognize that the system has been changed, because these runtime attacks, that is a general term for them, they reuse the code which is already in the memory of the application. So that means they don't change the code. So, and this is where the control flow integrity comes in. So this is a software solution where you guarantee that a program is following the control flow graph, or let's say the execution path, as it was intended. So control flow integrity is primarily a software solution. However, you still need an anchor. You still need some trust in another component, because for control flow integrity, you still need to store some sensitive information that should not be changed by, for example, an adversary which is currently trying to compromise your computer. So, and this is why we still need some trusted component, preferably in hardware, because attacking hardware seems to be, at least for many years, we believe that it is more difficult than attacking software. So this is the control flow integrity, and control flow attestation comes from the idea that control flow gives the real execution of a code, and the traditional attestation could not really, so to say, capture this feature. That means the behavior of the code. So if the code is running, you want to know if it goes through the path that was intended by the designer of software. So control flow attestation takes this attestation idea and applies it to the execution path of the software, checking if this execution path is benign according to what was designed, or it is deviating from its actual execution path.
So you've been working on control flow attestation for a while now. So what challenges are you trying to solve as part of the Assured project?
So in Assured project, we are trying to solve a problem which is still not solved, and that is how can you attest, or how can you verify the integrity of a complex software, like, as I said, like, for example, a browser or operating system or a server software running in a remote server. How can you verify the integrity, the integrity of this software, but as I said, in such a way that complies to real world. So the typical attestation proposed by many IT enterprises that are kind of summarized in the so-called Trusted Computing Group, TCG, that was proposed many years ago, was that you just calculate, so to say, a mathematical function over the binary code, and then the trusted component on your device, which is called the trust anchor, reports that to a remote party. So a remote party knows, oh, the system has not changed, has not been changed. But there are a number of problems with that. A mathematical function, a cryptographic function like a hash function, you hash the code, assume that there is a mathematical operation that compresses this code and creates a random number and random looking number, so to say. I'm just explaining it very simple. So, and then this number is signed by the trusted component and sent to a remote party who is asking for it. Now, given the most, so to say, the more sophisticated attacks that do not really, so if the hash value is changed, if this compression is changed, then, or this authentication is changed, when the binary code is changed, then the function will be changed. So, and then you can recognize, oh, there is something has been changed. Now, the sophisticated attacks, they don't change the binary code. So the report is always the same, but the attacker is running on your system. So to capture this, you need to capture the behavior of the program. And the behavior of the program is reflected mostly through its execution path. So, and that is why, so to say, this control flow attestation comes in, and in Assured, we want to do it for complex software. And for complex software, it is very hard because we want to do it in an efficient way. That means the party which asks for this attestation protocol, saying, asking the trusted component on your computer, hey, give me an attestation report. This attestation report is so to say at runtime. That means your computer or your trusted component must be able to calculate a kind of function of your execution path on your program, and then send it, report it to the party that is asking for it. And this is complex because a complex software has lots of execution paths, and reporting this is one thing, but also verifying it is another thing. So that means on the side of the remote party, you also need to have the same, so to say, program graph to check, is this path belongs to the program graph. So this is a lot of inefficiency. You pay a lot of penalty. Of course, you also know that the program is running is really the program that you want to run. But in reality, in practice, you can't really wait so much time so that the verifying party is verifying the whole complex software as well to see if the reporting party is telling the truth or the program has changed. So there are a lot of technical issues that you need to solve to have a practical system, because we are not just looking into it on the conceptual part, but also on practical part. And now, just to make it more complicated, is that the practical part is that we want to have it faster and more efficient. And for that, we are trying to use the advancements, recent advancements in machine learning. What does it mean? It means that on the verifier side, where you verify this, the report of the computing system, on that side, we want to have a estimation. So we want to train models that can very fast estimate, yes, this path would practically belong to the real control flow graph of the program without having the whole control flow graph and comparing it. So without having really the whole reference value. That once the model is trained, and for that we need data, and this is what we are doing, then we can put the model on the side of verifier, and the verifier can kind of estimate, can say, here, definitely this one belongs to the real execution of the program.
And Assured is already approaching its midterm. Looking back at all these months, would you say that all the goals pertaining to the design of adequate security schemes been achieved? And maybe you could tell us also about the challenges you faced so far in the first half of the project.
So because Assured is a relatively big project, and there are a number of partners doing. Each partner is doing actually very interesting things. We have industry partners who are looking into this attestation part with even on their products because they need that as well in practice. So from the overall project, as far as I understood, the partners have been relatively good in what they have promised and what it was planned. So everybody is progressing. But the project that we are involved in, that means, for example, the aspect of trusted computing and the attestation. One challenge that we encounter is, as I mentioned shortly before, is to train the neural network to kind of estimate or kind of learn, is that a real program execution path or not. For that, we need a lot of data. So that means we have to train the model with lots of attack traces. We call it attack traces. So that means what could go wrong, what would be an attack, so that the model, the machine learning model, is trained to understand this is an attack and this is not an attack. So for that, we need to create a lot of attack vectors or attack traces, as we call it, to be able to properly train the machine learning algorithm. So that is more or less, I would say, an engineering problem, and but sometimes you have to have also ideas to create data for enough data for the training. But other than that, I think we understood how the problem is and how we, so to say, capture this behavior. But of course, to make it even more complicated, we are looking into the execution path. There are attacks that don't use the execution path and they are trying to change the data. That one is the next step that we didn't promise in the project, but I think from research point of view, is very interesting to look into it. So currently, our challenge is to have enough data that the training of the model is good enough, so accurate enough.
And before we wrap up, I wanted to ask you about one more thing. Lately, we have observed an emergence of an interesting concept, namely sustainable security. How would you say the assured technologies can help to achieve that, also considering the need to converge with safety?
Mm. So, of course, sustainable security is in general very interesting concept, and it is sometimes it sounds like a buzzword, and sometimes because it will be kind of um, misunderstood because of sustainable energy. But in general, philosophically, the idea is the following: how can we guarantee the security of our systems in a long-term manner? So if I tell you this is a, let's say, very simple thing. Let's take cryptography. Cryptography is a bit more mathematical, but actually it's the least problem that we have in, um, in security, because once the algorithm in encryption or signature, once it is so to say designed, and once you can prove certain properties, then that's it. But we are talking about complex computing systems that an adversary can manipulate, can compromise, and when the adversary compromises a computing system, your laptop, for example, then cryptography does not help you because they will access all the keys. So now, sustainable security tells us, maybe tries to answer the following question: can I have a certain guarantee that I build systems in such a way that they are flexible enough so that they are kind of future proof, at least for a certain time. So in the past, just to make a parallel to cryptography, because this is easier for people to understand, in the past people said, okay, this cryptographic system, for example, encryption system, has the cryptographic key has this length, and in the next 10 years this length of key would be enough. But when stronger, powerful computers come, then the length of key must be longer. And then quantum computing came, and they said, oh, now quantum computing could break all these crypto systems, so we have to have another cryptography, so to say. Yeah. The systems part is the same. You have a very complex system, let's say IoT system, devices are Internet of Things, the devices are connected to each other. Not every device has the same security aspects or security features. How do you take care that the whole system cannot be compromised? Think about critical infrastructure. So Assured is trying to solve part of this problem, or at least come up with ideas how to solve that, so that if we are permanently under attack, we don't have to always fix an attack, let's say fix a system against one attack or a class of attacks, and then in 3 months another attacks come. So can we build our systems, at least parts of it, in such a way, or the core of the system that is very important for security, can we build it in such a way that we have a long-term assurance of security, or that we can patch the system? So think about hardware. You cannot uh, patch the hardware as you want, but you can patch the software as you want. So if there are lots of hardware attacks which we are observing in the wild, that means there are hardware vulnerabilities, and smart people can exploit this by means of software. That is what was not the case 10 years ago. 10 years ago, people tried to attack the hardware by physically accessing the hardware. Now you don't have to do that, because there are some vulnerabilities that have become so to say public, and people can exploit them. Can you build hardware in such a way that you can patch it at any time? Because once you tape out the hardware, it is out there, and you cannot just change it. Maybe a bit of change of microcode here and there, but you can't really replace the components of for example, an Intel CPU just like this. So you need to, it takes a long time to produce a new one secure against certain attacks. So would that be possible to reconfigure this hardware at any time when there is a new attack? So this is sustainability. You can resist new attacks without replacing the whole system. That is the idea of sustainability.
Thank you, Ahmed. It was a pleasure to host you today, and thank you for
Thank
sharing more
you.
about the project.